Welcome to the Explainer. So back in 1971, a foundational paper took a look at the beautiful symmetry of electronics and asked a pretty bold question. What if a fundamental piece was missing? What came next was a proposal for a brand new building block for, well, pretty much every circuit we use. All right, let's really dive into this. To get it, we have to start with a puzzle that had been sitting right at the heart of circuit theory for decades. This wasn't about trying to build something better or faster. It was about completing a picture that just seemed strangely incomplete. You see, in the world of electronics, it turns out there are 4 fundamental variables that describe how pretty much everything works. I'm talking about everything from the smartphone in your hand to the biggest supercomputers on the planet. These are voltage, current, charge, and something called magnetic flux. And you can just think of that as the magnetic field's effect on a circuit. Let's call them the 4 main pillars of electronics, and it's the relationships between these 4 that define all the basic components we use every single day. And this is where that puzzle really comes into focus. Look at this. We knew that the relationship between voltage and current gave us the resistor. Easy enough. Voltage and charge, that's the capacitor. And flux and current gave us the inductor. But that bottom right corner, for decades, the relationship between magnetic flux and charge was just a question mark, a gaping hole in the theory. Then, in 1971, this paper from a circuit theorist named Leon Chua comes along, and he proposes a logical, scientific basis for what should fill that gap. And this wasn't some lucky guess. He deduced its existence from pure symmetry. It just had to be there. He called it the Memristor, and that name, a mashup of memory and resistor, is a huge clue to what makes it so incredible. I mean, think about that. A resistor that can remember. So the Memristor is the component that officially fills that gap. Its defining feature is this fundamental link between the total electric charge that has ever gone through it and the magnetic flux. In other words, it's a component that connects a circuit's past to what it's doing right now. And here's why that is a total game changer. Your standard resistor has a fixed value, right? It's the same today as it was yesterday. A Memristor's resistance, though, is dynamic. It actually changes based on the history of the current that's flowed through it. It holds on to a memory of what's happened before. But here's the kicker. Back in 1971, this was all just a beautiful theory. No one had ever actually found or built a physical device that worked this way. It existed on paper, kind of like a ghost in the machine of circuit theory. So what do? How do you prove something exists if you can't find it anywhere? Well, you build it yourself. Chua designed a symbol for his new component, and then, using regular old lab equipment, he built a circuit that would behave exactly like his theory said a Memristor should. And the result? It was completely unique. When he tested his creation, it produced behaviors that were, as he put it, peculiar, totally different from anything you'd ever get from a resistor, an inductor, or a capacitor. And this right here is the smoking gun. When you plot the voltage versus the current of his circuit, you get this amazing shape. A pinched hysteresis loop. This strange looping figure 8 pattern is the Memristor's unique fingerprint. It was the proof. This was a fundamentally new type of component. But this wasn't just some abstract academic exercise. Right away, Chua could see the potential for this brand new element to solve some very real-world problems. For instance, he showed how a Memristor could perfectly explain the super weird behavior of a device that was new at the time, called an ovonic switch. For years, nobody could quite figure out its quirky electrical properties. It was a real mystery. So, he demonstrated that if you feed a simple pulse into a circuit with a Memristor, you get this complex, delayed waveform coming out the other side. And guess what? It exactly matched the quirky behavior of that real-world mysterious component. The Memristor was the key to understanding it. And he didn't stop there. He also showed how powerful it could be for generating complex signals. For example, he designed a circuit that could create a perfect staircase waveform, which is a really useful signal in tools like oscilloscopes. So the big takeaway here is that with a Memristor, you could take a really simple input, like a basic square wave, and transform it into a much more complex and useful output. And that's something that was incredibly hard to do with just the 3 traditional components we had. But the paper doesn't just wrap everything up in a neat little bow. It actually ends with this fascinating and provocative thought that really sticks with you. Chua pointed out a really interesting problem. If you found a real Memristor out in the wild and you decided to test it like a normal resistor, you wouldn't get a nice, simple, predictable line on your graph. Oh no. You'd see a strange, complicated, looping mess. And this leaves us with the final, absolutely brilliant question. Could this fundamental element have already been built? Could it have been sitting in labs for years, but we just dismissed it as a faulty component or some weird anomaly because we were looking at it the wrong way? A mystery hiding in plain sight.